Okay, so I'm going to try to break down this quantum version of a k nearest neighbors algorithm, um, which is used in clustering, is used in machine learning a lot as well. Now, there's different versions of sort of quantum ideas for the for a KNN algorithm, and I'm not an expert in the KNN algorithm, but this one here in particular, and again, so here you've got the authors. This is taken from ResearchGate. This one in particular uses the is it called the Hamming distance? I think it's the Hamming distance, which basically it's the metric they use for measuring similarity, which is nothing else than Hamming distance. Exactly, it's nothing else than traditionally like an XOR. So these strings here have a distance of 3. Let me see, I can pop the tools here somewhere. No. Has a distance of 3 because it has 3 bits which are different. The last 3. This 1 1 0 0 0 1 here. Okay, good. So and so here they describe the algorithm. There's a preliminary step. Preliminary steps. So it's basically 3 steps, which is I think those the first step 1 and 2 I think happen out of the. So extract the feature of the training set and store them as bit vectors by exploiting whatever. So this is just transforming your data into bit vectors and then map them into quantum bits, to qubits. So 0 into state zeros and 1s into 1s. And so what they say is then you've got at the end like a your training set is like a set of vectors, and then step 3 is construct a training set superposition. So that's where let's see where they're going with that. Let's see where they are going with that. They construct a superposition of equal probability. Okay, where we've got the vectors. Okay, but those are the features. Okay, so they encode in one entire state. But that probably requires a lot of qubits. I mean, because if I understand this well, this is basically telling you that each of these feature vectors, V, P, and then you've got a state where it's like you have the different feature vectors and you have at the end the class. Cool. So the main steps are input a testing sample, taking the same method to transform it to a quantum state. So input a testing sample. Good. So now you've got a testing sample, which is of the same form, like this here, of the same form. For some reason, I can't use my painting tools now, so I don't know. Sorry for that. But so okay, so main steps. So okay, so main steps. Input a testing sample taking the same method to transform it to a quantum state. X, a normalized feature vector. Okay, yeah. So basically, it takes the same thing here. Prepare the unclassified quantum state in the first register. Prepare the training set T in the second register. Prepare an ancillary qubit 0 in the last register. The result can be written as this. Okay, yeah. So basically, you've got like an. So basically, you've got a. That's interesting. Yeah, okay, you've got this. I think that what's interesting here is that so they're using the superposition to basically encode all the training set. So this is I think one of the advantages they're using here. One of the quantumness they're using because they're creating a superposition, and then you have the quantum. Okay. So let's see what happens. I'll try to build that step 3. So until here I understand that. So what they say here is they basically say apply a C naught in a way that the x, so it's a C naught x to the what I understand these are the things in the superposition. So first is I'm just do it naively. I'm gonna say here we've got our superposition 0, 0, 0, 1, 1, 0, 1, 1. And so here the qubits 0 and 1 are the training set. Then we will do a C naught. So we will assume that the input we have here is, let's say, 1, 0. 1, 0, like this. And then so this is basically the thing, so apply a C naught in a way that, so the A is the one that's A is the target, so it's B. So this should be, this should go here, right? And then there should be this one that goes here. Exactly. Yeah. Mm-hmm. So you've got 1, 0. So if you get 1, 0 here, that's the minus, right? Because we just have 1, 0. If you've got 1, 1 and 1, 0, yeah, exactly. 0, 0. Yeah, so that works actually. Okay. So now we've got here the result of this minus each of the elements of the superposition. And then say that then we negate that, and it's supposed to be a trick. Let me put the identity here to make it easier. So then we negate that, and we're gonna keep the identities here as well. And so far at the ancillary level as well. And then step 4, so that's step 3. Step 4, in this step we'll compute Hamming distance in terms of these, and label the k nearest neighbors of the testing sample, modify the corresponding ancillary qubit 0 to 1. According to a distance threshold, this operation can be, the operation of this step can be defined as a certain unitary operation which realizes the equal superposition, of this plus this with the ancillary qubit. So here, if I understand this well, isn't that the same as just adding a Hadamard here? So you now have, so if that's your ancillary qubit. Examine distance between x. In step 3 is record the difference in the corresponding position I. Hence the Hamming distance can be computed as the sum of these. As we recall, in section 2 we introduced a quantum circuit of A equals A plus 1. Then the key step for adding D can be realized by taking advantage of the circuit in figure 4, which is the reduced as figure 4b. The algorithm is that we can initial is L plus D, and the condition of Hamming distance can be determined by whether the addition of D plus ancillary overflows or not. So there's, I think here there's a bunch of, okay. Once the addition is done, we select the most significant qubits and use quantum OR gate to get the signal conda P, which indicates a condition. The quantum OR gate is shown in figure 5. Boo. D plus A. So what they're saying is that if we set an initial A equals L plus D, so this, okay, so this A, so it seems like this is just a trick to get to know which of these results kind of are below a certain threshold. So it's just a mathematical trick by defining an A that is equal to L plus T, and this T is the threshold, and L is 2 to the K minus N, which is N times in step 3 the cross difference. Hence the Hamming distance can be computed as we recall in section 2 we introduced a quantum circuit of A plus 1. Then the key step for adding D can be realized by taking advantage of this circuit as figure 4, which is just figure 4b. Yeah, that's just the just A plus, like it's like the addition circuit. Just how you would implement an addition of A plus D. I think I understand, but I'm trying to. Basically, this A, it kind of tells you, so you have to define it in a way that it just tells you if you add. Okay, so then you can determine simply. I know what they're trying to do. So the condition, because you want to select the ones that have the Hamming distance lower than a certain d, right? And the trick here is you have them in a superposition. So you've just now basically what you've done is you have them in a superposition, and here you've got the minus. So the result of massing each of them, right? So you've got this exactly. So you basically have got in each of those possible states. It's pretty smart actually. In each of the states, you've got the two lower beats encode the one of the elements of the training set, and the following two encode the result of minusing your input, which is in this case 1 0, against that particular element of the training set. So now you're going to filter that and say, okay, so I want only the ones that are below a certain threshold in terms of their Hamming distance. And the way this is defined is they're just proposing to do this in a way where you add a constant, you add some A to these D's in a way that if they overflow, then it means that the Hamming distance is there. And you're gonna do that overflowing. It's pretty damn smart. And you're gonna do that overflowing. And once the addition is done, we select the locked in most significant qubits and use quantum OR gate to get the signal, which indicates the condition of Hamming distance. Mm-hmm. So I'm not so sure if I'm implementing step 4 correctly though.